Okay guys, I wanted to give you a quick video just to show you how to work this is called a hybrid circuit. It's neither series nor parallel, although parts of it are series and parts of it are parallel. But just to give a quick run through what this problem asks is, what's the power delivered to each resistor? So you've got a bunch of resistors here, and you know that the power is always IV. And for a resistor, for each resistor, if you knew the voltage across the resistor and you knew the current to it, you can write this as I times IR, or I squared R, which is the more familiar formula you'll see in the book. So our job in this problem is really to first understand that there are different currents in different parts of the circuit. Anywhere where you see a junction, you're going to have a new current, and then figure out how to find those currents. And we're going to do that by reducing this circuit. Okay, so the first thing to do is to look for resistors that are in series. Look for resistors that are in series. That means try and find resistors that don't have junctions between them. So for example, these two don't have junctions between them. These two also don't have junctions between them because I can take this path through the battery and there's no junctions. That means that I can reduce both of those resistors. So I'm actually going to do that. Let's do that. So I'll redraw my circuit. I still have a 10 volt battery. That doesn't change, 10 volts. And then for these two circuits, when you combine circuits in series, the equivalent resistance is R1 plus R2. So I'll draw both of these guys just as one resistor right here, and 10 plus 5 is 15. So this is 15, okay? And then this 30 ohm guy, I'm not going to mess with yet. Let's just leave him alone. This is 30 ohms, okay? And then meanwhile over here, I reduce these two. 10 plus 5 is 15. Okay, so now I have this circuit, and I can now say, all right, are any of them in series? No, because there's a junction here, which means that the 15 and the 30 are not in series, and neither are these in series because they also have a junction between them. So then the next question is, are any of them in parallel? Are any in parallel? Remember, parallel means same voltage, same voltage. And the way you can tell if two things have the same voltage is if you make a complete loop all the way around a circuit, and those are the only two things in that loop. So if I do this, I go all the way around, and after going all the way around, there are only those two things. It's not just two resistors, only two things. So those are the only two things there. They are in parallel. So I can reduce those. How do I reduce resistors in parallel? Well, 1 over REQ equals 1 over 30 plus 1 over 15. So I'll get, this becomes 3 over 30. And so REQ is 10 ohms. Okay? All right. That means that I can reduce my circuit further. The 10 volt battery stays a 10 volt battery. This round, I haven't messed with the 15 ohm resistor at all, so that'll stay 15 ohms. But now those other two have reduced to 10 ohms. Now I ask myself the question again, are any in series? Well, yes, as a matter of fact, now after all that hard work, there's no more junctions between these two resistors. And so as a last final step, I can reduce this to something that looks like this. So again, these are in series. So I add them, REQ equals R1 plus R2 for a series combination. And so that makes this 25 ohms. 10 volt battery, 25 ohms. Okay, so why did we do all that? Well, the purpose of doing all that is because now we know that across this 25 ohm resistor, I have to have 10 volts. Why do I know that I have to have 10 volts across that 25 ohm resistor? Because the battery gives each charge 10 volts. Those charges make a complete loop and are required to spend all 10 of those volts by the time they get around, and there's only one place for them to spend it, here. So that means that now I can use Ohm's law. I can only use Ohm's law once I know the voltage across the resistor. And now I know that it's 10 volts. So the voltage equals the current times the resistance. So 10 equals I times 25. And so the current I is 10 over 25, or 0.4 amps. Okay. Am I done with the problem? No. Am I making progress? Yes. So here's the next thing I can say. All right. This 25 ohm resistor, it's not a real resistor. The problem isn't asking about the power through that resistor. It's asking about the power through all these resistors up here. So what I now need to do is kind of work my way backward and figure out what I1, I3, and I2 are. The good news is actually that I already know what I1 is. How do I know what I1 is? Well, this is the wire that has the battery in it. That's what we just solved for. And apparently the wire that has the battery in it has 0.4 amps running through it. So immediately I can actually come up here and I can write I1 is 0.4 amps. Okay. Now, if I1 is 0.4 amps, that means, and I'll do this in a little bit, but not yet, I can find the power through this one and I can find the power through this one because all of those are in the same part of the circuit that has I1. What's left for me to do is to find I2 and I3. Okay. Okay. So I want to find I2, I3. How do I do that? Well, let's come back to what we know. We know that in this circuit, there's 0.4 amps. Okay. Well, this circuit came from this circuit and I haven't added any wires or anything. So there must also be 0.4 amps in that circuit because there's no new wires. There's no junctions. Any current I have in one, I have to have in the other. That means that if I wanted to, I could find the voltage across each of these resistors. So just as an example, the voltage across the 15 ohm resistor would be IR, or 0.4 times 15, or 6 volts. Oh, it's 10. I'm sorry, 10. I don't know why I wrote 15. Whoops, no, 15. Sorry, 0.4 times 15, which is 6 volts. Okay, that means 6 volts gets eaten by this resistor. Okay. Likewise, if I wanted to find the voltage across this resistor, I could say V equals IR, and that would be 0.4 times 10, in which case that's 4 volts. In other words, I know that all 10 volts have to be eaten, and I know that 6 get eaten here and 4 get eaten here. Okay, that's good to know. And the reason why it's useful for us to know is because think about it. 6 volts get eaten by this 15 ohm resistor. If an electron goes all the way around, it has to eat up all 10 volts that the battery gives. So I've already said that 6 volts have to get eaten by that, right? Now, if I go across the 10 ohm resistor, it's the same as if I go across the 30 ohm resistor. Or it's the same as if I go across the 15 ohm resistor. Because we've said that if an electron gets 10 volts from the battery, it loses 6 of them on the 15. It has to lose 4 by the time it gets back to the battery. It can lose 4 by going across the 30, or it can lose 4 by going across the 15. Either way, it loses 4 volts. That is very useful information for us. Why? We now know that the voltage across the 30 ohm resistor is 4 volts. We are interested in the current. Well, current equals V over R. So that's to say that the current is 4 divided by 30, or 1 over 7.5 amps. Some amount of amps. Let me pause and I'll come up with a number just so it's not. Okay, so that's 0.133 amps. That is how much current goes through the 30 ohm resistor. But wait a minute, that's I2. So I2 is 0.133 amps. Now there's actually 2 ways to get I3. I'm going to do it the sort of naive way, and then I'll show you why there's an easier way to get it. But let's first do it the same way we did the first one, just to show you that the same technique works every single time. So we also said that there are 4 volts across the 15 ohm resistor. So let's find the current there. I equals V over R, and that's to say we still have 4 volts if we cross the 15 ohm resistor divided by 15. In that case, it's going to be twice what this one is. So 0.2666. That is I3. I come back up to my diagram. That's I3. So I found it for the 15 ohm resistor, but the 15 ohm resistor was made up of the 10 and the 5, and I didn't add any wires in order to make that, so I must have the same current there. That means that I3 is 0.266 amps. Okay, now what was the other way? I said that I could probably find I3. Well, if you think about it, whatever current is in I1, it gets split between I2 and I3. That means that as soon as I know I2, I can immediately say I3 equals I1 minus I2. Or to put it another way, these two have to add up to give me this one. Okay, so that is how you find the currents. There are lots of tricks and stuff people can use for this problem, but I don't want to focus on those. I just want to focus on like brute force. What can you do that will work on every single problem? And these techniques will work on every single problem. Okay, so what does the problem ask? Find the power delivered to each resistor. So, okay, we have how many resistors? 1, 2, 3, 4, we have 5 different resistors. So the power delivered to the 5 ohm resistor is I squared R. So that guy has I1, so that's 0.4 squared times 5. The power delivered to the 10 ohm resistor down here, that is 0.4 squared times 10. I'm going to pause, fill out the rest of this chart. Okay, so I did all the grunt work. I worked out I squared R for each resistor, and I wrote them over here. And if I add up the power dissipated through all of the resistors, I end up with, up to rounding errors, about 4 watts. And the question is there any way to know where, after doing all of that work, is there some quick way to check whether or not my answer is correct? And actually there is. All of the power that gets delivered to these resistors, every single joule that goes to all of these resistors has to come from the battery. And so if we can find the power output of the battery, it should be equal to the sum of all of the power dissipated by the resistors. That means the power of the battery is IV. Well, the current the battery puts out is 0.4. 0.4 times 10. Holy Toledo. 4 watts. 4 watts from the battery, 4 watts delivered to all of the resistors. Okay, so hopefully this is more helpful than confusing. Feel free to ask questions if you have them.